Hey everyone, today I'm going to break down one of the most fascinating parts of compiler design, code generation. If you've ever wondered how your source code turns into something your computer can actually execute, you're in the right place. So, what exactly is code generation? Think of it as the grand finale in the compiler pipeline. After all the parsing, analyzing, and optimizing, this is where the magic happens. The compiler translates your optimized intermediate code into target machine code. That's right, the actual instructions your system's processor understands. But it's not as straightforward as just converting one line to another. The generated code has to be correct, efficient, and optimized for the particular hardware it's running on. Otherwise, you could end up with slow programs, bugs, or even code that won't run at all. Let's quickly go over the main goals of code generation. First, correctness, the most important thing. The output code must do exactly what the original source code was meant to do. No more, no less. Next, efficiency. Nobody wants slow software, right? The generated code should run fast and use minimal memory. Finally, maintainability and portability. Good code generation should make it easier to debug, extend, and adapt the program for different machines. So what does the code generator need before it gets to work? 3 things. The intermediate representation, usually in some 3-address code format. The symbol table, which tells the compiler where things are stored and their types. And the optimized code, fresh out of the previous compiler phase. These guide the code generator in producing the right instructions. Now, let's see how the code generation phase typically works. First, instruction selection, choosing which machine instructions to use for each operation. Then, register allocation, deciding which variables should go into fast access registers and which should stay in memory. After that, instruction scheduling, reordering instructions to get the best performance. And finally, assembling it all together and emitting the actual code. To make things clearer, here's a quick example. Suppose your intermediate code is T1 =a plus BT2 =T1 asterisk C. The assembly code might look like movi R1, a ADD R1, B mul R1, C movi T2 R1. See how each high-level operation gets mapped to specific machine instructions? But code generation isn't all smooth sailing. There are real challenges, like a limited number of registers, handling complex data types, instruction set restrictions, and making sure it all works with the hardware. That's why projects like GCC and LLVM are constantly working on improving their code generation engines. Also, code generation often follows an optimization phase, which cleans up and simplifies the code. For example, if you have x =, a plus 0, asterisk 1, the optimizer turns it into x =, a. The code generator then produces much more efficient code. So to wrap up, code generation is the last but one of the most crucial stages in a compiler. It transforms optimized intermediate code into efficient machine instructions, ready for execution. And it relies heavily on everything that comes before it in the compilation process. If you found this video useful, hit like, share with your batchmates, and subscribe for more deep dives into compiler design and programming concepts. Any questions? Drop them in the comments. I'm always happy to help.